Could the AI be used to say, hey, this is shockable with 80% accuracy or stuff like that? Or not only that, but hey, this is shockable because this is the peak that looks weird on the ECG.
Welcome to MedTech Unfiltered, the core science podcast where we talk about real challenges of developing and improving complex medical devices.
So welcome to another episode of our podcast. This time we'll be talking a bit about ventricular fibrillation, ventricular tachycardia, and how AI is used to tackle these regular issues within the AD aspects, some of the regulatory challenges also. We have an expert with us. Halil, do you want to introduce yourself?
Yeah, I'm Halil Özer. I'm an algorithm developer and a software developer here. And for our AI part, it's especially used in our devices, so it has a special focus using the AI as we do it. And we do it in a very critical circumstances, very critical devices, so it has its special considerations and special constraints.
Yes, so Halil has been a developer for many years here at Core Science. He's one of our go-to guys whenever we have very complicated issues to tackle. So that's why we have him here. And what you mentioned just at the beginning can bring us into, let's say, our first question or starting question. How is AI used for analyzing VF or VT in general? How is it different to the traditional methods, I would say, that I think they utilize thresholds and more traditional definitions? Can you explain a bit about that?
Yeah, sure. The traditional methods, like rule-based systems overall, where the developer of this algorithm just sets the features and the characteristics which to analyze, and then sets the thresholds and sets where to say this is VFVT or no. In an AI model, the AI model itself learns these characteristics itself. This is done by training data, labeled training data, so there's always a training step before, so that the AI model is trained, and then afterwards it can be used for the real detection thing.
Yeah, so it's a classical way of training AI before deploying it, I would say.
Yeah.
And the traditional methods are, as you mentioned, rule-based. There's a threshold, and you define the steps for the computer to say it's VF or shockable or not shockable in our case, right? In case of AEDs.
Yeah.
Would you say there are advantages to using AI, for example, on these topics, or?
Yeah, there are some advantages because in the traditional way, the rule-based things, the developer has to think about what is important, where do you have to look in the signal to say this signal has an VFVT rhythm. So you have to have much knowledge base, medical knowledge base, or so for doing it, and maybe he can make some mistakes or some misassumptions. In the AI world, it learns, as I said, itself. This characteristics are important, and so it sticks to the data you get within it, and it's labeled data, so you know it is shockable or not shockable. When it learns the characteristics, and when it says, okay, this might be correct or not correct. So we assume that the probability of the detection, higher detection rates, is more with a classical AI method than with classical rule-based systems.
So what I understand there, at least from my non-software developer mindset, is that it opens the possibility, or it's easier to train an AI system to detect VFVT, because I don't need all this knowledge that a developer would need to set these thresholds, right? Yeah,
that's true. That's the thing. So you just take the data, the labeled data. Okay, it's not just, it has another restrictions we can talk about. But then we just give it to a model. The model is trained, and the model just makes all the things itself. It just sets the inner threshold, the inner methods itself, and that gives you the result. In the traditional methods, then you have to think also this, how does VFVT shape, for example, look like, and then just think of characteristics, describing this mathematically, making some mathematical models, and then just implementing them and seeing if this is correct or not.
Yeah. So it does take a bit more of a work, I would say, without it. I just want to, I mean, you mentioned data at some point, and this is a very important topic in all the AI topics, you know, the classic garbage in, garbage out. Now we're talking about labeled data, which was, I would say it's an AI thing. Can we talk about more about it? How hard is it to get data, for example, in terms of ECGs? How is it used for training?
So the data part is a very, very important thing for AI. So as you said, garbage in, garbage out. And it has to be made with responsibility, with a high responsibility. First, you have to get the data. This might be hard. It depends on the questions, especially for VFVT. It's not so easy to get the data. There are several restrictions, like you have to get the data from the devices. You don't have access to the devices. Or if you use the clinical parts, you have to just contact them, and they also have to get the data out of the devices. And there's another big thing, that the security of the personal information of a patient is a big thing. So you can't just take everything else, and it's so there's to do some pre-processed data, making much time, but regarding information of patient, regarding the data itself. So, and another point is that the data you get has to be somehow representative. You shouldn't get not the data from 80-year-old man. It's not representative. So it should be from, I don't know.
So all the ranges of ages.
All the range of ages.
You know, male, female.
Male, female, and also from different regions, not also white Europeans, also from Asia, from Africa. This would be the best way. So it's preparing the data for training is topic itself. So it's
as you mentioned, it's like a whole topic. It could be a whole project, right? Just to get the data to train an AI. And I agree. So I identified from what you mentioned a few challenges. So getting the data directly from devices. So here, I guess, collaboration between companies that deploy AEDs would be like the first thing. Hey, we need you guys to provide us with the ECGs for your past 200 missions or something, right? Because there you have a lot of shockable or non-shockable. That would be your labeled data, right? So this ECG was not shockable, and so this ECG would be shockable.
The labeling itself is done by the experts, not from us. Surely we have to do at least 2 experts, medical personnel or doctors that say this is shockable and this is not shockable. So we have also, again, to have a cooperation between the medical people and us.
So that's the first one. Then there's the regulatory aspect. So in EU, that's pretty strong, data privacy. I kind of remember there are some basic processing steps that remove this. I think there's 7 not articles, but labels that need to be removed from data, like, you know, the patient name, things like that, right? To make it
it's at least so. You have also to talk to the which is allowed or not in the special case, but age is mostly okay. Female, male, might be also okay. Then that's it. No, most times.
Okay.
So you don't have any other information about the person, about thing that can lead to this person.
Yeah.
It might be, I don't know. He has black hairs. It's not allowed because might be in somehow we can just with another information see that this is the person you get. So all the information that can lead to a person for patient has to be deleted.
From a technical perspective, are there data points that you need from this information that is kind of censored? Would any of this, I mean, probably not the hair color, but any other data that could be helpful for our application of BFBT that is normally censored? Is there anything you would like to keep from exam?
So as many information as we have, the
more the better.
We have, the better is. So the ECG is clear, but what might also help is information about medical treatment or about diseases, other diseases or something like this. Maybe he had a heart attack before and then now he has in VFVT or something like this. This might also help to categorize this ECG and to help make more information.
Yeah, I was reading that there are some studies. I mean, for this you need the whole clinical record of the person, right? And that's definitely not going to be analyzed within the second when you're in a mission and the device is analyzing, you know, the ECG, right? This might comes afterward. But I think there were some guys gathering all this information, and they trained an AI which could I think it had 70-something% accuracy to say, hey, this person is at high risk of having a heart attack within 2 weeks. I mean, of course, it didn't say it's going to happen on Thursday at 3 p.m.
Yeah.
But it gave you a very good window, and
So that's the fact. Or if you have other informations aside from the ECG, you can just give the AI model some a priori information, so that it can just weight its self decision another way than just giving the ECG. Yes.
How do you see, for example, AI being used directly in the current workflows? Like when we talk about AEDs, I mean, they're very automatic, right? But there's also the profi defibrillators, which are used by trained personnel, you know, the people in the ambulances or the doctors. Which, from my perspective, I mean, this is kind of like a second opinion, right? So if you have the device, in the end, the doctor is the one that decides if the shock should be delivered or not, right?
Yeah.
Could the AI be used to say, hey, this is shockable with 80% accuracy or stuff like that? Or not only that, but hey, this is shockable because this is the peak that looks weird on the ECG. Yeah. How do you see it?
It's very exciting thing. I think this is somehow the second generation VFD detection algorithms. And this is possible by AI, because the AI just makes most time a decision and somehow gives this percentage about how reliable is this decision. So you can just get directly at feedback, and also the other things are yes. I think this is somehow the future. AI in the medical devices are also, especially in the VFD detection, yes.
So we've been talking about how AI is trained. How does it work differently than the traditional methods of, you know, threshold and rule-based? How this all falls within the workflow of the medical industry, I would say, the doctors, the ambulance users. We also briefly talked about data, how it can be biased, for example, how we need huge amounts. I think that's a question that a lot of people have. How much training data do you need, right? Can you give us like a few examples or numbers that a company that wants to develop their own AI model need to look into?
Yeah. So you have to have data for training, and you have the data for validation and testing. So it's something of a testing, for example, part. This is when you just have a regulatory effect, where you have clearly defined numbers given from regulatory part from norms. So we have to be at about 200 shockable signals, VFD, and then some 100 non-shockable signals. This could be normal sine rhythm, other things, and so on. So this is just for the testing part.
Yeah.
And so we develop then the training part, the validation part, you just again need there is some parts of it.
And I think we briefly talked about it outside of this podcast, but what about synthetic data? Like, can this be used for training? Can it be used for validating? Why yes, why not?
I think it can be used, especially for corner cases like high rates with normal sine rhythm, 300 ppm or something. It is not. I think we don't see it in the real world, but this could be a training data it can be used for training. It's, I think, allowed to use such data. Also, you can just use real data, add some synthetic amounts of like noise or something. Let's just shift it or something like that. I think this is a common features using data or generating data for AI. I think here it's also allowed to do it here.
And just because you mentioned noise right now, I kind of have the feeling, or from what I was reading, so AI tends to perform better under noisy conditions, which is, I would say, the normal scenario for AEDs. Yeah. So I mean, with AEDs, we're talking about devices that you need to be used in the moment wherever you are, you know, the train station or the park, and these are also used by people who are not trained, right? So you have a lot of situations where, for example, the pads are not correctly attached, so that brings noise. And AI seems to handle those scenarios better, right? Or
yeah, it's better than a normal deterministic way, just with rule-based way, because for each noise type, if you use it in a rule-based system, you have to think of it before, and it's just, but you can't think of all maybe noise that can be there in the real world. So, but if you have the training data with different noises, and you would expect, or something like that, the AI system can just can be trained on this, and we can see, this is noise, and so we just somehow have better results than the normal.
I think this is one of the amazing things of AI in general, not just for ECG, but it just picks up on information that might be lost by us, right? So can consume vast amounts of information and say, hey, this is noise, right? This is not relevant. Kind of, because I mentioned it earlier for one of the studies on predicting patients with high risk. But I also saw some guys, I don't remember the university, but they took ECG data, like the already, after it had happened, the whole situation. And they could predict like a heart attack with 30 seconds of a window. Which, I found that like impressive, because technically, I mean, I guess on the traditional methods, you have your curve, ECG curve, and when you start seeing this aberrations, or there's no pattern or something like that, that's when it triggers, right? But these guys using AI could identify 30 seconds before, which is not a lot, right? But
not a lot, but might be the threshold between.
Gives you time to sit down. Maybe call 911.
Sure, that's it.
I mean, this is very important statistics for the people that are not familiar with shockable scenarios and heart attacks. I think every minute counts, right?
Every minute, every second counts. So it's really important.
I think per minute you lose like 10% chance of living. So if you're like 7 minutes without, an ambulance, then you're mostly gone, kind of.
And if you have the FVT rhythm or VF rhythm right in the moment, and then every 5 seconds counts. So if you then just 5 or 4 seconds, it's really important that the detection algorithm is really fast. Doesn't need that. You don't have time to say, okay, here's a minute and just let's analyze it.
Yes.
You have to be within a few seconds. You have to have a result.
And I think AI is it better at that? Does it need less time to determine, hey, this is shockable than a traditional method, or no?
This is not in general. You can't say that, but you can just develop such AI systems that are really fast. Because you can just give them, say, okay, this is my amount of data with a few seconds, and just check this, train with this ECGs, for example, and just itself then just checks it and analyzes the characteristics within a few seconds, and comes to a model that has high detection results. So I think it's easier to come to a fast system with an AI system than with a rule-based system. Yes. Okay,
so it does sound promising. That brings me to another challenge, the regulatory challenge. So AI, of course, at the moment is like a big buzzword. Everybody wants to use it. I think there's even AI toothbrush, they're putting it everywhere. But from a regulatory perspective, particularly within the EU, I mean, we have the MDR, regulations. There's the AI Act, which I think it's already enforced. There are other, complementary regulatory topics being drafted. And what I see is that basically AI is being treated as a fixed software package, which once you release it cannot be touched.
Yes.
And with AI, I think one of the main advantages is that you can continuously train it.
Yes.
So it can learn. How do you see this?
I'm somehow you mean just learning on the device? So I'm critical on that, learning on the device, because of a system that's learning on its own in the device that is used, we can't predict what this will happen, what it will learn. But now the usual way is just to train the model offline, come to a model, then let's say, this is my model, and this is then fixed. And this fixed model is then implemented in the device. So,
and this is what you register when you go to your notified body and say, hey, I have a new model. And it's fixed, right? So there is
It's
no further
fixed.
changes.
Yes, there's no further changes. And as you said, the MDR and the AI Act, I think there is defined that in medical devices, model should not be trained or is not allowed that is trained anymore. Or it should be fixed in the device. And so it has a fixed behavior. You know how it behaves and not think it. You can just, again, offline train it and make a better system and then just go push it to the device, but not on the device itself.
So not continuous training. There's something I think it's a bit different in the FDA market. Mm-hmm. So they have like a tool called PCCP. I don't know what it means. I don't remember the acronym. But it basically allows companies like us, Core Science, saying, hey, we developed this AI model. It determines if a shock is required or not. But it allows you to update it. It kind of, let's say like this. So FDA approves not a software package, but approves a process. Okay. And within this process, you can say, hey, every 6 months, we're going to update our algorithm and it affects this and that aspects of the device. So it's kind of a bit more flexible. I think because also AI regulations in the US are also more flexible, right? So they do see AI as a living thing that it keeps evolving, while in EU we have more, strict phases. Yeah. So I think that's a challenge. Definitely, there's going to be some, I don't want to say conflict, but there are differences between how companies will handle this in the US market or in EU. I think definitely, UK is also attached to our EU regulations. Okay, so we've been discussing a lot about the regulatory aspects. For example, how does the FDA handle it? How MDR or the EU handles it? What I wanted to ask you is a bit more about the insights of it. So yes, from a regulatory perspective, on a regular software, you kind of document it, you release it. And from these traditional methods that we talked, there's very specific rules defined by you guys, and hey, this is the threshold that we're going to be using because of this and that reasons, right? With AI, it's mostly like a black box, right? So how is it handled by your side, like on the development perspective? How do you document it even? And how can this be a challenge for the regulatory part?
So for the regulatory part, we want to know if the system you have developed is safe and how the system works. So if it's safe, you can just test it with data. And the question how it works, it's harder to explain with AI than rule-based, you're right. But there are some approaches like the explainability of AI systems. This is a research topic itself, so it looks into the AI model, checks what does the AI model take from a signal, which parts, and what does this analysis of this parts lead to a decision to, on which amount is this part important for the decision. So you can just step by step analyze the inside of such an AI system. This is also somehow an important part, yes, because you have to somehow surely to show the regularity part that you know what the system does. It's not just a black box, you just fit data and then just get an answer. So it's also important if you just, for example, get some data and the result is not that you have expected. And you just you should have a capacity to analyze why did you get to this result and what improvements can I do on the system to avoiding this result.
Yeah, but it's perfect that you mentioned this whole AI transparency topics. So it is definitely a big area of research at the moment. And accountability, which is how MDR defines it, I think is very important within the EU market. I think in general, right? You want to know if your device fails, why did it fail, right? So it's definitely a topic to keep an eye on. One other topic I wanted to ask you about was, we've talked about how hard it is to get data, how it is used for train. Can we use synthetic data to train models? We touched a bit on the regulatory aspects also. What about the hardware limitations? How hardware needs to be adapted to fit AI models within an AED? For example, Core Science, we're at the moment working on the smallest AED in the world.
Yeah.
Can it fit an AI, for example? Stuff like that. Right?
This is an important question. So the AI model you use has to fit to the hardware you use. You can just use some hardware that is somehow prepared for AI topics, but you can't make your device so really big or big powerful as it may be for the most powerful AI model. So you have to strict the AI model to the hardware. So the hardware gives the circumstances of like how complex this AI model can be. Complex in the sense of computational power consumptions and in the size of this model. So you have to just really check beforehand what model or what AI model can you use in that hardware. There are several approaches to simplify your model, like for fitting into the hardware, but it is somehow limited. So you can't simplify your model so far that it always will have the detected results as before. So this is an important thing, so that you have to use the hardware first that can work with the AI model. There are for example, more powerful controllers or some dedicated AI controllers, something like this. But again, your AI model has also to restrict to your hardware, so the hardware gives a model somehow.
So with the risk of going a bit too much into this technical, would you say if I want to use an AI model into my device, I need a different processor, for example? Is the energy consumption kind of doubled, or I mean, it also has a bigger footprint on the PCB, I would guess. I mean, there's a lot of hardware changes, right? But I guess they're also more expensive in general. What are the things that change there when you're designing a device that wants to fit AI models into it?
Again, depends on which AI model you want to use and which is the topic of that. Do you use which detection result you have to expect? You must fulfill. For example, for our case, for VFET model, you have to check that your controller is fast enough. It has somehow enough memory. So the thing is that you should also have enough memory, because AI models fastly grow up and they may need some memories and also the computational power. So the thing is, if you just want to use in a device, the controller you can use should be more powerful than
a regular.
Or there are also some controllers that have an AI core. This is also a thing that you can solve a problem, but you should use the controller or use the hardware, especially that can be capable of AI systems.
So there you have it. We've been covering a few very important topics in AI within the aspects of AEDs. So we talked about data, how is it used to train, why is it so hard to obtain. We touched a bit on the regulatory aspects also of releasing AI models into the market within medical devices. And also we talked about the hardware limitations. How do we need to adapt our design of devices? Halil, thank you for coming. Thank you for joining us. Yes, follow us.
Subscribe to MedTech Unfiltered so you never miss an episode, and find more resources in the Core Science Academy.